new kind of section that we'll start on today. And let me minimize this. Okay. So in this section, we're going to talk about graphs of functions. I think we're actually starting a brand new chapter in the textbook. So instead of thinking all about how to find derivatives, how to evaluate derivatives into a function, we're going to start thinking about what the functions actually look like. So I know we spent a little bit of time on that, but we haven't spent too much. Okay. Now, before we even start talking about max and min functions, I'm going to try to tell you why this is important, and then we'll come back to this later. And the whole goal of this section is to introduce this idea called optimization, which are problems that tell you to find like the max and min of something. So for example, I don't know, a can manufacturer wants to know what's the best shape that minimizes the cost of manufacturing, or what's the maximum acceleration that a spacecraft can do. Okay, so really cool types of questions that can be answered using calculus involve things with maximums and minimums. Okay, now, of course, this is a calc class. We have to put names to things. So I'm going to try to introduce some definitions for you, and exactly how to say these definitions, the correct notation for it, and all that stuff. Okay, so here we have a graph. Okay, looks like it curves up and down here. Let's talk about how I could describe this graph in words. Okay, if I were to say describe this graph depending on how high it goes, what would you say would be like the absolute maximum of this graph? 5, right? Anyone say 3? Okay. Let me go back to that fact. Okay, so let me just write out what I just said here. Okay, I asked you to find the absolute maximum of the graph, and everyone said 5, and I think we can all agree that this point here is the absolute max. That's how high it goes. There's nothing higher. Okay, so there's 2 ways I can describe this point. Okay, I can say that this is either 5. I could also say it's f of 3, right? So let me write that up. F of 3, and that's 5. Okay. So when I talk about the absolute maximum, the greatest value that this takes on, I can either describe it in terms of its x value or in terms of its y value. Okay. I can't say that the absolute maximum is 3 though, because it's very confusing to say, is that the x value or the y value? Okay, so whenever we talk about how high a function goes, you're either going to write one number as its y value, or in terms of the x value, but f of the x value. Does that make sense? Okay. Can I pass this back over? Let's talk about how we can say the absolute minimum. Okay, I think we can all see that the absolute minimum is here, right? Function goes down that far. Okay, can someone give me one way to state this point as the absolute minimum? F of 6, right? F of 6 would work. Another thing I could say is what value? 2, right? 2 is the y value. Okay, so I can either say the x value as f of that value, or I could say the y value. What wouldn't work, okay, don't say that 6 is the absolute minimum, because it's very confusing to say, okay, is that the x value, is that the y value? We always refer to the minimum and maximum in terms of the y value, so how high it goes. Okay, so I put this in red, and it's the formal definition of an absolute maximum or minimum. I'm not really going to make you memorize this definition or anything. I think it's way easier to think about this more conceptually in terms of examples than with the definition. But one thing I want to point out in this definition that I copied from the textbook is I'm going to call this either the absolute or global maximum. So whenever I use those 2 words, I'm talking about how high does the entire function go? How high does, or how low does the entire function go? Okay. Another word I might use for this is the extreme values. Okay, so anything that talks about absolute, global, extreme, we're talking about how high the function goes. Okay, now just a slight warning that I think I've drilled into your heads. These extreme values, the absolute max, absolute min, these are always going to be the y values. Okay, so never state that an x value is an extreme value, because if we mix the x's and y's, then we're never really sure what number is which. Okay. Any questions on absolute max or min? All right, let's flip our page. Let's see how this can get a little bit more complicated. Okay. So example one, we want to find the absolute max and the absolute min. The last example was a little bit easier because it happened like where the point or where the function had a peak and where the function had a valley, and it only happened at one point. Let's see what can happen when there's multiple points going around here. Okay, so let's do the absolute max first. Okay, how can I say the absolute max? Well, what number is the absolute max here? 16, right? That's how high the function goes. Now, the function reaches 16, not at one point, but at 2 points, right? So the absolute max happens here and it happens there because that's how high the function goes. Okay, so other ways I can say this, I can say f of -2. I could also say f of 2. Okay, but I usually like to go with 16 because it's very short, simple, nice too. Okay. Any questions on the absolute max? Okay, pretty self-explanatory. Okay, let's talk about the absolute min. Okay, what's the absolute min here? -10, right? That's how low the function goes. This point right here represents the absolute min. So -10. Another way you can say this is f of 3. Okay. Now that's kind of weird. Last time the absolute min happened at the valley and the absolute maxes happened at the peaks. Why isn't this guy the absolute min? It's not the lowest y value, right? The absolute min doesn't talk about like a valley or a peak. All it talks about is the highest x or the highest y value and the lowest y value. That's all we're interested in. Okay, let me pass this out real quick. Okay, so that's all absolute maxes and mins mean. How high does the function go? How low does the function go? Okay. Now, let's go down example number 2. This is a little bit more conceptual, and I want to label some values on this graph here. Okay. Now, I'm not going to ask you this because I think it's hard to say in words, but it looks like the absolute maximum of this graph happens up here, right at the very peak of the graph. Okay, so this definitely represents my absolute maximum. Okay, and how can I say that in terms of like a number? F of d, right? F of d is how high the function goes at x equals d. So our absolute maximum here is f of d. Okay, what's the absolute minimum? F of a, right? That's how low the function goes. So this is the absolute minimum. Okay. But there's a lot of other stuff going on here, right? There's a lot of curves, a lot of peaks, a lot of valleys here. I want to put some names on other things as well. Okay, now going from left to right, it looks like this point here is a peak. I think we said a long time ago that whenever we have a turning point, the derivative is equal to 0, right? So this is definitely an important point, but it's not the absolute maximum. It's definitely a maximum because it turns around, but it's not the highest point, okay? Now, because it's turning around, we like to call this the local maximum. Oh my gosh, I can't spell. Local maximum. Okay, and what this means is it just means that around this value, this point is the highest in a certain range, right? So it looks like it turns around here. Okay, so our local maximum here is f of b. Okay, so same sort of way that we say our answer here. Okay, now the derivative doesn't have to equal 0 at a point for something to be a local or maximum or minimum, because over here we have a sharp corner here, right? So here it looks like my function goes down. Okay, now this is an example of a local minimum. And that's because around this point, it looks like that's the lowest it goes, and then it kind of turns around. Okay, so we would say f of c is a local minimum. Okay. Let's go back to this point that we said was the absolute maximum. Okay. Would this also be a local maximum? What do we say? Who says yes? See some yeses. Why would it be a local maximum too? Yeah, it turns around there. Around this point, it looks like the function turns around. It is the highest point in general around x equals d, right? So this is actually both a local maximum and an absolute maximum. Okay. So some terms, we can have a local and absolute max at the same point. Okay, let's go down to this point here. This point doesn't look like it's the lowest point, but it definitely is a valley, right? It turns around at this point. So this is another local minimum. Okay, so f of e is my local minimum here. Okay, now we had an absolute maximum here, and we have an absolute min. Is this absolute min a local minimum? This one's actually a little bit tricky. Okay, I'll let you think about it too much. It actually depends on the textbook. The textbook doesn't consider this a local minimum. I don't know, really know why. Okay, but I'm just gonna write, don't worry about endpoints. Okay, because it really depends on the textbook if this is a local min or local max. So I really don't care too much. Okay, so don't worry about endpoints. Depends on the textbook. Okay, if you go on to further math classes, some textbooks will be like, oh, that's a local minimum. And some textbooks will be like, I don't count that as one. Okay. Any questions so far? All right, let's flip our page over. I'll give you the precise definition of a local max and a local min according to our textbook, okay? And I know this sounds really crazy. Let's just kind of go over and see what this is saying, okay? F of c, where c is our x value, and f of c is a y value, okay? We're going to consider this y value a local max if for any x around c, so for x values within a range of c, like within this blue area, okay, if f of c is bigger than that blue area, all the y values in that blue area, then we're going to call that a local max. That's all that's saying. Now, I don't expect you to memorize this definition. I don't think it's very useful for this class specifically, but I just have it there just in case you wanted a refresher. All right, let's go to example number 3. Okay. Now, I think this might be overkill, but I promise all these different examples are a little bit different. So let's go through these and figure out what we're doing here. Okay, so we have this graph of this function between -1 and 4. I want to find any local extrema and absolute extrema, which is just asking me to find the maximums and minimums. Okay, let's do the absolute ones first. So absolute maximum. Okay, what is the absolute maximum here?
F equals -1. Well,
Or
-1.
f of -1, right? So you're talking about this point here. Another way you can say that is by saying 37. Okay. Just a little note, I think WebAssign takes the number. I don't know if it takes f of something. So if you're typing this into WebAssign, you can try it out, but just to be safe, I would choose the actual number. Okay. All right. Can there be any more than one absolute max? No, right? Absolute max is the largest point in the entire graph. There can't be more than one, so we're all good. Let's move to the absolute minimum. Okay, what is the absolute minimum of this graph?
Got a sneaking suspicion it's -27.
And your sneaking suspicion is right? This point right here is the lowest that the graph goes. So either f of 3 or -27 would work. Okay, so WebAssign, you would probably type in -27. Please don't write 3 because 3 is not the absolute minimum here, right? It's -27. All right, let's move into our local minimum and maximum. So let's do the local maximum first. Okay. What are my local maximums here? Any ideas? Actually,
Oh, wait, don't worry about it.
I wouldn't worry about the endpoints yet. Yeah, that's technically not one according to our textbook, but it is tempting to write that. Yeah, 5 is one, right? Definitely 5 is this point here. So f of, oh gosh, oh no. Oh, wow. Here we go. All right, f of 5, or sorry, f of 1, which is 5, is a local max here. Okay. Now, local min. What's my local mins here?
0,
0, f of, oh yeah, I didn't even think about that one. Well, I didn't write that one down in my paper, but yes. Looks like f of 0, which is 0, is a local minimum here. And it seems like we have another one over here, f of 3, right? I can't believe I missed that one in my notes. Wow. All right. Okay, looks like we found everything. We found all our valleys and our peaks. Any questions on example number 3? All right, let's flip our page over. I'm gonna go over 4 more examples with you because there's a couple things I do want to talk about here. And then I'll let you do one on your own, I promise. This might seem like overkill, but I promise there's little things that can happen here that I do want to talk about. Okay, so this example is asking us to find any local or absolute extrema on the graph of cosine x on its entire domain. Okay, what's the domain of cosine x? What x values can I plug into cosine? Yeah, anything, right? The domain of cosine is all real numbers. Another way you can say that is negative infinity to infinity, right? So that's what cosine looks like. We want to find every single extrema of cosine on its entire domain. Okay. So let's draw out cosine. I think drawing a graph is the best idea to figure out absolute extrema with the tools that we have right now. So drawing cosine, I guess we need to draw like 0, pi over 2, pi, 3 pi over 2, and 2 pi, right? But it goes on further than that. Okay. What's cosine of 0? I think I heard it. It's 1, right? Cosine of 0 is 1. Okay. What's cosine of pi over 2? I think I heard it. Not quite 1. What does the shape of cosine look like? Doesn't it look like this? Okay, so I'm guessing it should go down. Why don't we come back to pi over 2 then? What's cosine of pi? -1, right? So cosine goes down like this, okay? So if cosine is going down, and we know that it passes through the x-axis somewhere, what do you think cosine of pi over 2 is now? 0, right? It goes like this, right? Now, continuing on the shape, what do you think cosine of 3 pi over 2 is? 0, good. And what's cosine of 2 pi? 1, good. Okay, so cosine, remember, it has this wave-like shape, but it starts at 1, and it kind of looks like a U if you only graph this part of it. So I wonder if my drawing skills are pretty good here. Here we go. And it just continues the same shape over and over again. Okay. All right, let's talk about local and absolute extrema here, okay? Let's do the absolute ones first. So absolute, what's the absolute max of cosine? 1, right? It's the highest that the function goes. Now, this happens at both x equals 0. It also happens at x equals 2 pi. It also happens at x equals 4 pi, right? So it happens at every multiple of 2 pi. But because I'm lazy and I don't feel like writing that, I'm just going to write the number. Okay, I know that cosine goes highest 1. I don't have to write it in terms of f. So absolute max is just 1 here. Okay, let's do absolute min. What do you think the absolute minimum of cosine is? -1. Cosine doesn't go below -1. So that's my absolute min. This happens at pi, 3 pi, 5 pi, any odd power, or not power, multiple of pi. But instead of writing that out, I'm just going to write the number because that's easier to do. Okay. What are my local maxes and mins going to be? So where are my peaks and valleys going to happen?
Every local maximum is the absolute.
Yeah, right. It looks like my absolute maxes happen when the function has a peak. And it looks like my local mins also happen when we have a valley. So it looks like the local max and min are also going to be the same. So this is my local max. And this is also my local min. Okay. So sometimes local maxes are the exact same thing as the absolute maxes. Sometimes the local mins are exactly the same as the absolute mins. Okay. Any question on cosine? Okay, so we introduced trig functions. Let's go down to just regular functions here. Okay. Example 5, we want to find the absolute and local extrema for x squared on its entire domain. What's the domain of x squared? That's the range. Negative infinity to infinity, right? All real numbers or negative infinity to infinity. I can plug anything into x squared. Okay. Now, just sketching the graph of x squared that we know looks like a parabola. So it looks like a U. Okay. Let's figure out extrema here. Let's start with absolute. Let's start with the absolute max. What's the absolute max of x squared on all real numbers? Doesn't exist, right? There doesn't actually seem to be an absolute max here. Doesn't seem like this function really stops anywhere. It just keeps going up and up and up. So right, so this is actually an example of something that does not have an absolute max. So we don't actually have to have these. Okay, so I'm just going to write none. Oh gosh. Okay, so there's actually no absolute max here. Okay, what's the absolute min? 0, right? It looks like at x equals 0 and y equals 0, there actually is an absolute min, happens right at the center. So we can either say f of 0 or 0. I like writing the number because WebAssign takes it, but we can write it in terms of the X value as long as we write it with F in front. Okay. Let's do local maxes. Any local maxes here? No. I heard 0. 0 actually seems to be a min because it looks like a valley, right?
Oh.
You're doing math.
No, there's no local max.
Yeah, there's no local maxes here, right? Because, well, there's no peaks here. Looks like the graph just goes up and up and up. So this is an example of something that doesn't have any local maxes either. Okay. What about local mins? 0, right? 0 is a local min as well as an absolute min. Okay. 2 more examples for you. We're going to do example 6 and example 7, and then I'll promise I'll let you try one on your own here. So let's do this one here. We want to find the local or absolute extrema for f of x equals x cubed on its entire domain, which is all real numbers. Okay. What does the graph of x cubed look like? What does that one look like? Looks like the Disco Man, right? So if I were to draw this, it would look like this, and then it goes up like this. Okay, let's talk about maxes and mins here. What's the absolute max here? What's the highest point that this function goes? Yeah, this function doesn't really stop at any point. It just keeps going up and up and up. So this is an example of something that has no absolute max. Let's talk about absolute mins. Okay. What's the absolute min of this function? There isn't one, right? This function goes down and down and down, and it doesn't stop anywhere. So this doesn't have an absolute min. Okay. What about local maxes? Any local maxes here? No, right? This doesn't seem to have any peaks or even any valleys, right? So I actually think this doesn't have a local max or a local min, right? There's no peaks, there's no valleys. So there's no maximal, no local max and no local mins. Okay, so this is an example of a function that does not have an absolute max, an absolute min, or a local max or a local min. So you can have a function with nothing in it either, or yeah. Any questions on these examples so far? Good. All right, let's make things a little bit more complicated, okay? Here we have a function with a lot of stuff going on, okay? Let's go through this real quick. So there's some stuff that I want to talk about here, okay? Let's talk about absolute stuff first, because I think that's a little bit easier to work with. Okay. What do you think the absolute max of this function is? Let me add numbers here. 5, right? This function goes up to this point here, and that y value is 5. Okay, so 5. Another way you can say this is f of 1, 2, 3, 4, 5, 6, 7, f of 4, right? Okay, but 5 usually works. Okay. Let's talk about absolute min. Okay, what do you think the absolute min is?
1.
Okay, I hear 1, I hear 2. Anyone want to explain why it might be 1? Because it does, it has a limit approaching 1, but does it ever reach 1? No, right? Now, of course, there's values above 1, so like 1.000002 is a point on here. So the function does go down here, but there's an open circle here, which means the function doesn't actually reach 1. Okay, now I'm going to tell you what this one is. This is an example of a function with no absolute min, according to the textbook. Okay, so if there is a open circle as our endpoint, this is an example of something that is not an absolute min. Okay, it's not considered one here. Okay, now it really depends on the textbook, so I wouldn't like think too hard about this because some textbooks would probably consider this an absolute min, but according to ours, this doesn't have one. Okay, any questions so far? All right, let's do some local maxes. Okay, this one's a little bit fun to work with. What do you think our local maxes are?
5.
Definitely, wait, 5, yeah, definitely 5 is a local max. It definitely has a peak here, so that's a very obvious one of a local max. So f of 4 or 5 is definitely a local max. Okay, any other ones? Oh, I hear 4. And there's actually 2 places where we have 4. We have this point here and this point here, right? Which point are you talking about?
On 6.
F of 6, right? F of 6 is a place where the function is higher than everything around it, which is our definition, right? So this is an example of a local max. Okay, so f of 6 or 4 is a local max here. Let's talk about the other point. Is this point here, is that a local max? No, right? Because there is a open circle here, okay? But there is a closed circle, okay? What do you think I should call that one? It's not a turning point, but is it a number that's lower than everything around it?
Yes.
Yeah, so what do you think I should call it? A local min, right? So this one's a little bit weird, but this is an example of a local minimum because it's lower than all the points around it. And that's kind of the definition that we're using. Okay, so we actually just found a local min here. Okay, we know that f of 1 or 3 is a local min. A little bit weird, but that's kind of what our textbook uses in terms of local maxes and local mins. Okay, any other local mins? 2 or yeah, x equals 2, y equals 2. This is also an example of a local min. Yeah.
That also, wouldn't that be the absolute minimum? No. As you said, we don't have that points.
Oh, which one? This one here?
Yeah, for example.
Oh, the absolute min is the lowest that the function can go. Now, this point's definitely lower than it too, right?
Yeah.
But then this point's lower, and this point's lower, and this point's lower, and this point's lower. So technically, the lowest place this function goes is like around there. But since there's an open endpoint,
So we
yeah,
don't have points.
yeah. Now, with absolute min, let me give you an example here. So you don't have to do this in your paper because I feel like you'll mess things up. But let's just say, let me change things up here. Let's just say I took away this entire part of the graph. Okay, no, don't do that on your paper. What would be the absolute min now? It'd be f of 2 or f of 0, right? Because there's a closed endpoint there. Okay, now endpoints don't count when it talks about local maxes and mins, but endpoints absolutely do count when we're talking about absolute max and absolute min. Okay. All right. Okay, so I think we said f of 2 was a local min, right? Which was 2. Any other local mins? F of 5, right? This is an example of a local min as well. Okay, so f of 5 or 3 is another local min. I guess I wrote 3 twice, so I really don't have to write 3 again, but f of 5 definitely is a local min. Okay, I think that example was a very crazy example. I think it took everything into context here. What I'm going to have you do is I want you to try example 8 now. I think either 7 or 8 is on the homework. I don't remember which one, but I'm gonna give you a few minutes to try example 8. Try to find all the absolute local maxes and mins, and we'll come back in a little bit. Oh, looks like we got some stuff on the board here. Let's go through that real quick here. Okay, so we have this funky graph. We want to find the local and absolute extrema for this one. Now, Blake wrote up the absolute maxes and mins. Do you kind of want to explain your thought process here?
Yeah, so at F0, there's an open endpoint, so there is no absolute max. The
Mhm.
absolute min is 1. Is that F0? There's the lowest point.
Yeah, right. So you find your lowest and highest points. As I was walking around, I don't know if I saw this too much, but there should only be one answer for absolute max and absolute min, right? So you should only have one thing, either none or one number for those two, because we're talking about the highest point and the lowest point, and that's it. Okay. Let's talk about local max. Mason, do you want to talk us through your thought process here?
So within two certain ranges, the absolute max was 4,
Mhm.
3. Those 2 humps.
Uh-huh.
And then the local minimum were the in between the both humps, the point where it is. I'm not even describe it. Like,
It kind of like goes off the function, like it jumps off, right?
yeah.
Yeah.
And then point between them, which is low.
Yep, works for me. There was one thing I wanted to say about this. What was I gonna say? Trying to remember what I was gonna say about this. Okay, maybe I'll just come back to it later because I do not remember what I was gonna say. Nice job on this one. Does anyone have any questions about example 8? All right, honestly, with these funky graphs, I would definitely give you a graph and ask you to find the absolute maxes, absolute mins and stuff like that. I would say with these crazy functions with all like the jumps and the valleys and stuff like that, I don't know if I would technically quiz you on it. I would definitely ask you homework on it, but I would definitely want you to know how to find something more like examples 3 through 6 instead of these examples. Okay. Any questions so far? All right. Moving on here. I think we have enough time for this. So I forgot to write this down. Okay, so we're gonna move into a very important topic after this involving maxes and mins. And before we do this, I actually want to challenge you to get a little bit creative. I would like you to draw a function that satisfies 2 things, okay? I want you to draw a function that is continuous on a, b. Okay, so a and b are 2 x values, and they have to be closed, so there shouldn't be any open intervals at the end. Okay, so there should be filled in endpoints. Okay, so our function should look something like this. Okay, no open circles at the end. Okay, and once you're done doing that, I want you to find the absolute min and the absolute max. Okay, now it has to be continuous, meaning you can't take your pen off the page. Okay, I want you to draw one of these functions, and I want you to get a little bit creative. Okay, I want you to try to draw something that might not be thought by anyone else. All right, so we got pretty creative here. We have all these different graphs. I think that's about as many graphs I can think of. I can't think of a graph that would have any different features than these. We had continuous functions on a closed interval. Continuous means you can draw it without picking up your pencil. Function means passes the vertical line test on a closed interval, which means the endpoints are closed. Okay, I don't think we have enough time for this in this class, but next class we will find the absolute maxes and absolute mins of all these graphs. And then I'm going to ask you a question that might make you think about things a little bit harder.